dive right into today's explainer, where we're going to demystify the seemingly intimidating physics concept of projectile motion. Have you ever watched a basketball arc perfectly into a hoop or a baseball just fly into the stands and wondered about the hidden mathematical rules guiding that exact path? I mean, it looks incredibly complex, but today we're going to break it down into simple, highly intuitive building blocks. To make this super easy to grasp, here is our roadmap. We're looking at vertical motion, ideal horizontal motion, understanding 2D motion, velocity vectors, and finally the impact of gravity. Let's get right to it. All right, part one, vertical motion. We'll kick things off with something you've probably done a million times, tossing a ball straight up. Picture tossing your car keys straight up when you're bored. You launch them with a max initial velocity, let's say 10 meters per second. But the exact second they leave your hand, gravity starts pulling, right? So that upward velocity steadily decreases. Then, something kind of magical happens. Right at the absolute maximum height of the throw, the velocity drops to exactly zero. It literally stops midair for a split second before gravity takes over completely and the velocity ramps right back up as it falls. Up, stop, down. Pretty straightforward, right? Moving on to part two. Ideal horizontal motion. Let's completely put that vertical stuff aside for a sec and look at the exact opposite. Rolling a ball perfectly flat across the ground. Now, in our everyday real world, you roll the ball and it eventually stops. Why? Well, because the ground pushes back with friction and the air pushes back with resistance. But if we put on our physics glasses and imagine an ideal scenario where we just totally ignore friction and air resistance, what happens? Without any of those forces pushing back, that ball is going to keep rolling at the exact same constant speed forever. It would literally never slow down. Which brings us to part three, understanding 2D motion. The real magic happens when we mash these two isolated actions, moving straight up and moving straight forward, together at the exact same time. So imagine an object moving forward on the x-axis and upward on the y-axis simultaneously. It isn't just going up, and it isn't just going forward, it's doing both. This simultaneous combo is exactly what we call projectile motion. Because it's moving forward at a steady clip while doing that whole slowing down on the way up and speeding up on the way down routine, it traces that beautiful, perfectly curved parabolic path we see in sports and nature. All right, part four, velocity vectors. Let's look at a concrete mathematical example to really build our understanding here. And don't worry, we are keeping the math super intuitive. Imagine you throw a ball at a 20-degree angle with a starting overall speed of 50 meters per second. In physics, we don't just treat that 50 as one big number. Instead, we use some basic trigonometry to slice that throw into our two building blocks. Using standard sine and cosine, we reveal that a 50 meter per second throw at a 20-degree angle is actually made up of 47 meters per second of pure horizontal speed and 17 meters per second of pure vertical speed. We've successfully split the atom of our throw into its x and y components. And finally, part five, the impact of gravity. Now that our perfectly split ball is actually flying through the air, we really need to figure out what forces are trying to mess with it. This is where things get fascinating. Think about this ideal scenario for a second. The ball leaves your hand, and we're totally ignoring air resistance. How many forces are actually acting on that projectile as it arcs through the sky? What do you think? The answer might actually surprise you. It's literally just one. The moment it leaves your hand, there is absolutely zero forward force acting on the ball anymore. None. The only force acting on the entire system is the downward pull of gravity. And honestly, this brilliantly illustrates our core takeaway for projectile motion. Let's connect the dots here. Because gravity only pulls straight down, it only affects the vertical y direction. There are absolutely zero forces acting in the horizontal x direction. And because there are zero horizontal forces, that horizontal speed stays completely, perfectly constant. Meanwhile, the vertical speed is totally at the mercy of gravity, slowing down on the way up and speeding up on the way down. Let's watch this play out with our earlier numbers. At launch, we're moving 17 meters per second up and 47 horizontally. As the ball rises, gravity fights it. So the vertical y velocity drops to 9, but the horizontal x velocity still 47. At the absolute max height, the y velocity hits exactly 0, but the ball is still relentlessly cruising forward at 47. As it falls back down, the vertical velocity becomes a negative 17, while that horizontal speed stubbornly remains exactly 47 meters per second for the entire trip. This actually completely busts a super common physics misconception. A lot of folks think a thrown object momentarily comes to a complete standstill at the very top of its arc. But as we just proved, there's no way. The ball doesn't stop midair at its highest point. It only momentarily stops going up. It is aggressively flying forward at its constant horizontal speed the entire time. To tie this all together beautifully with Newton's laws, we essentially have two completely different worlds coexisting in a single throw. Look at the x-axis. It's a peaceful zone of zero net force, zero acceleration, and constant unchanging velocity. In stark contrast, the y-axis is entirely ruled by the net force of gravity, taking on constant negative acceleration, resulting in a constantly changing velocity. Projectile motion is literally just these two independent realities happening at the exact same time. So, we've perfectly mapped out our ideal physics world. But here's something to chew on as we wrap up this explainer. If perfectly constant horizontal velocity only exists when we completely ignore air resistance, how do you think real-world engineers calculate the exact landing coordinates of a returning spacecraft or a missile, where friction and wind are very, very real? Think about how many crazy dynamic variables have to be added to this perfect parabola to bridge the gap between ideal math and our messy atmosphere. Until next time, keep questioning the physics of the world around you.